Yeah, Assalamualaikum warahmatullahi wabarakatuh. My name is Lutfi Hakim bin Rasuludin. And my supervisor's name is Dr. Waida Binti Idris. I'm doing research based on time predict heating of Rayleigh-Bennet convection. So we're gonna go to this straight to the point, which is the methodology. So the method I did research is from journal titled Time Predict Heating of Rayleigh-Bennet Convection, written by Badauria 2002. So in this slide, in this slide and the other next slide will show the methods. So first of all, Bosnick's approximation, the first part, this part is only to show the governing equation, which is 2.1 and 2.2 are the governing equation. Meanwhile, the temperature 2.3 at below, we can see it, temperature equals to temperature M in the kurungan, dalam kurungan 1 minus alpha in bracket T minus Tm. That is the given equation. So second part of this method, model for wall temperature, which means that this model for wall temperature is easily symbolized by this three equation, or what we call this by this system TT, right? Next is the Fourier series. Fourier series, this Fourier series, there's many given equation, and figure 2 is the variation of temperature T with time T. Yeah, how we found the how we want to find this graph is based on the 2.5 and 2.6 and 2.5a. We can sub the 2.5a, 2.5b and 2.5c including 2.5 in order to get this figure. So at the function wall we have two condition. First is lower boundary and the upper boundary is modulated. So the first condition is shown at this equation 2.7a and 2.7b, and the second condition is which is upper boundary is fixed and only lower boundary temperature is modulated. So in this second condition, 2.8a and 2.8b are given. So 2.9 is the coefficient that are given. Next, diffusion equation. Diffusion equation, this part is only to show you how to find the temperature, which is in 2.11. So these are the coefficient equation given in not coefficient. These are the equation that are given in in two in this journal 2.12 and 2.13. These two equation given in order to get the 2.11 temperature. So these are the coefficient in 2.15 and 2.16 below this. We use this coefficient to 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 transform our governing equation into linear form, which are formed in 2.17 and 2.18 and 2.19. So these three equations 2.17, 18 and 19 are formed because of we sub 2.15 and 2.16 into the governing equation. Then we will get the these two equation. So this is the explanation after we transform it into the linear form. We transform the governing equation into the linear form. Non-dimensional frequency, uh, the temperature gradient obtained from the dimensionless form of 2.11 and 2.20 and 2.28, and these are the equation that are given on the in the journal. 2.22 and 2.23 are also considered as non-dimensional frequency. Now taking care of 2.17 twice and using 2.2 and 2.3, we get the system as 2.24. The boundary condition for the rigid wall are given by W equals to 0 and Z equals to Z plus minus half. So this is the add or the my further research in doing in FYP2. I studied, I do Galerkin technique. Galerkin technique transform the PDE into ODE. So the equations that are involved by this process are 2.24 and 2.25. Then the coefficient that have in 2.24 and 2.25 are given in this section. 3.1, 3.2, and 3.3 are the coefficient of also 3.4. So these are the four coefficient of equation in 2.24 and 2.5. When we define the temperature, the equation of 3.3 and 3.25 in a manner so that uh, these two equations will vanish at z equals to plus minus half, and then it will produce 3.5. So 3.5, now we substitute 3.1 and 3.2 into equation 2.25 and 2.5, then multiply 2.24 by 3.3 and 2.25 by 3.4. The outcome of this system is L equals to 2n. ODE for the unknown coefficient A and T and B and T. So 3.6 and 3.7 are the 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 3.6 and 3.7 adalah hasil derivation yang dilakukan apabila kita sub 3.2 and 3.1 and 3.2 into 2.24 and 2.25. So equation 3.6 and 3.7 are ODE equation. Sorry. Then these three equations are the coefficient in 3.3 and 3.7, which are given in the journal. So start from this, we may use the law of Simpson. For computational purpose, it is convenient to rearrange the 3.6 and 3.7. For this, first we must multiply the equation 3.7 by the inverse matrix k and m minus a squared. I don't know what symbol is that, and m. And 3.11 are the hasilnya. Now equation 3.6 and 3.7 can be written in the form of 3.12. For now, we may use classical Floquet theory to discuss about the stability of solution. We use 3.3 13, 3.13 solution. Then the initial condition are given, which is 3.14. 3.14. Then we have to do some rearrangement in the constant matrix, and the then we the when we arrange the matrix C eigenvalue produced, which is 3 point matrix C 3.15, we produce an eigenvalue, and the eigenvalue in produced in 3.16. So the values of characteristic exponent determine the stability of the system. We assume that that symbol are ordered so that then the system is stable to one periodic solution and represent a stability boundary. This periodic disturbance is the only disturbance which will manifest itself at marginal stability. To obtain the matrix C, we have integrated the system using Runge-Kutta-Gill procedure. The matrix C eigenvalue are calculated using the Rotishauser way. Result and discussion that so as shown that 4.1 are the results after we rearrange, we sub, and we use the law of Simpson. We use Galerkin technique, and we rearrange equation. We sub the equation. We will get the 4.1. The value of RC have been calculated for the following three cases, which is the first when the plate temperature are modulated in phase, phi equals to 0. Second is plate temperature are modulated out of phase, phi equals to pi. And last but not least, when the bottom plate temperature is modulated, the upper plate is held at fixed constant temperature. So it is true based on the value RC we can control the heat convection. However, it depends on the solution also. For instance, we need to modulate one of the plate temperature according to the phases. Thank you so much.